Okay, guys, thanks everybody for coming to today's colloquium. So our speaker is Sam Coogan from Georgia Tech. He has appointments in the EE and civil departments there. He did his PhD at Berkeley in the EECS department, got his PhD in 2015, and then he spent a year at UCLA as an assistant professor before moving to Georgia Tech. He's the recipient of the IEEE Transactions on Network Control Systems Best Paper Award in 2017. And he primarily works on formal methods and controls applied to transportation systems. So.
Yeah, thanks a lot for the introduction, Lily. So I'm very excited to be here. Today I'm going to talk about formal guarantees in traffic flow networks. And so I'll have to explain to you what I'm after when I say formal guarantees. And then, as you'll see, we'll be applying these techniques to kind of various problems in traffic flow theory and traffic flow networks. So let me just begin with a little bit of motivation and a video that I took. So this is actually a video in LA at night, obviously. So this is Sunset Boulevard, a famous kind of major arterial in LA. This is the famous 405 interstate. And you can see quite a bit happening in this time-lapse video. You can see, obviously, a lot of traffic flow happening here. You can see congestion waves propagating based on the taillights. There's a traffic signal over here, and so you can see queues kind of forming and then dissipating as the light turns green. There's a few ramp meters. So here's a ramp meter device here that controls traffic flow. There's a couple other ramp metering devices up here and over here. And so you can see that even in this kind of small picture of what's happening in this particular network, it's actually pretty complicated. And in fact, if you watch this particular car right here, he just made an illegal U-turn. So not only do we have to reason about what cars are doing in the network legally, we also have to think about sometimes the human in the loop and think about what the human brings to the picture as well. So the purpose of this video and some of these stats is to show that this is a huge problem, even on this kind of small picture, understanding what's happening here, understanding how traffic is flowing around in this picture, and understanding if you want to ask yourself, what can I do to improve this situation? How can I control this network better? I think it's apparent that there's a lot of different problems you have to reason about and think about along the way. So there's a growing need for this efficient transportation systems. So the good news, I would say, is on the flip side of some of these negative statistics and this apparently daunting task, is that even though traffic flow is a very old problem, there's a lot of new opportunities that are presenting themselves that allow us to bring new tools and new ideas to this domain. And so here I've highlighted what I consider to be sort of the three major thrusts that we're seeing that give us these new opportunities. The first is that we have real-time wireless sensing all over the transportation infrastructure. So we see that with cars themselves acting as probe sensors in the network. We see this with actual wireless sensors embedded in traffic infrastructure in roads themselves. Increasingly, we're seeing vehicle-to-vehicle and vehicle-to-infrastructure communication capabilities. So not only are we sensing this, but we're able to communicate, which gives us the ability to close the loop around these sensors. And these DSRC radios that you may have read about are becoming more common on commercial vehicles, and in theory, they'll be on every commercial vehicle within the next few years or so. Unclear if that's really going to happen, but certainly the technology is moving in that direction. And then, of course, kind of the hottest topic today in the media is this idea that we're going to have new autonomous capabilities in these cars, which kind of add an entirely new dimension to the control paradigm here. So we're going to have cars that are able to do some things on their own, certainly, and then, depending on how optimistic you are, can end up doing a lot of things on their own in the very near future. So all of these are going to present new opportunities and also new challenges for controlling these complex systems. So another aspect of this, another side to this problem is that this is going to bring us a ton of data. In fact, probably an overwhelming amount of data. Like so many systems in the real world these days, this amount of data is going to quickly become very difficult to deal with. And so I think here the challenge is that we need to understand how to best make use of this high resolution streaming data that we have from vehicles and infrastructure. And then maybe kind of in addition, and I'll talk a little bit about this towards the end, we also want to understand how this data and how this information, how we should tie this into other societal scale systems that are going to interact with this, what you might call a smart city scale, right? So this is now a buzzword as well, this idea that you have these interacting smart infrastructure pieces in this large smart cities context. And I want to drive home 2 points on this slide and throughout the talk. The first is that data should augment and not supplant these model-based approaches, right? So it's a bit of a cliche these days to say, oh, let's just take a bunch of data, throw it through some sort of learning algorithm, and then we can probably get something useful on the other end. I'm going to argue in this talk that I think there's a lot of insight we can get by taking a model-based approach to dealing with this data, and that we shouldn't view this as an opportunity to get rid of models and just focus on data. I'm going to argue that we want to use the data with the models that we have. And then the other thing I'm going to argue in this talk is that the models you choose, they're going to be most valuable when you choose models or when you derive models where there's some sort of inherent structure in these models that reflects something physical, something phenomenological about the system that you're trying to capture. And so in traffic flow, for example, I'm going to make this point that we can use certain types of models to capture, for example, congestion propagation. And so I think it's an important piece of the puzzle. And so when you combine these two ingredients, these model-based approaches that elucidate inherent structure in your system, this is what we're really going to be after in this talk. So let me sort of highlight what I sort of consider the state of model-based approaches to traffic design right now. So you sort of have two main categories of traffic models when you're talking about how we understand how traffic flow theory works. So on the right, we have microscopic models. These models where you're actually tracking individual vehicles in the system. You're paying attention to maybe their fuel consumption, their speed relative to the vehicle in front of them, these sorts of things. And on the other complete side of the spectrum, we have these macroscopic models where you're modeling some sort of aggregate quantities about the system. In an extreme case, you could be modeling, for example, the total number of cars in an entire city or in 2 neighboring towns and how that changes over time. A lot of times in the literature, you'll find that this is described as a clean dichotomy where you have either microscopic or macroscopic models. In reality, I think it's more instructive to think of this as a continuum, where on the one side, you could have very detailed microscopic models. This could be useful for understanding, for example, how long the yellow light needs to be at a traffic intersection to make sure that a vehicle approaching at the speed limit has enough time to stop before they enter the intersection, right? So this is a very kind of detailed model that you want to understand. On this side, you might be more interested in city planning type questions, origin destination type questions. You know, how have general traffic flow patterns changed now that certain neighborhoods are becoming more popular and have more people in them? You know, so there's sort of these macroscopic trends in the data. And then in between, you have a whole slew of type of models and for different purposes. I would argue a lot of the modeling, kind of the classical modeling in traffic flow theory, has operated more on the right-hand side of the spectrum to a degree, where you have models that track individual vehicles, and this opens the door to what I would call simulation-based design. So for example, here's a simulation, a microscopic simulation for a problem that I'm working on with some collaborators at Berkeley. I won't talk too much about this particular problem, but the point is that we can use these microscopic simulation tools to validate and check our results. In this talk, I'm really going to focus on this piece of the spectrum, something a little bit closer to the macroscopic side of things. I think this is an underexplored area that's ripe for bringing data to the picture and understanding the mathematical structure in these problems. And so what we're going to be after today are mathematical models that are going to be amenable to some sort of formal analysis so that we can say something concrete about the system without having to resort necessarily to these simulation models. Of course, it'll be nice to validate them in perhaps a more detailed model at the simulation level. But I'm going to argue that I think there's a lot of benefit to have by looking at models sort of at this piece of the spectrum. So that's where we're going to lie today throughout this talk, is models that are closer on the macroscopic side of things. So think understanding densities on lengths of networks, understanding kind of queue lengths and how queue lengths through a network change over time. These sorts of scales is what we're going to be looking at. So here's a brief outline of the rest of the talk. So we just finished the motivation and background section, and my talk is going to be consist of 3 primary topics. The first is going to be what I'm going to call a meta model of traffic flow, which we can use for modeling density-based traffic flow evolution dynamically over time, understanding how congestion is going to form and propagate on the scale of minutes or hours, understanding how traffic flow will behave. These types of models you're going to be able to use, I would argue, for understanding how congestion forms on a freeway during rush hour and then how it dissipates after rush hour, right? So that's the kind of models we're going to be after. I'm going to present a meta model for traffic flow that is very flexible in the sense that it can accommodate a lot of specific instantiations of however your traffic in your particular city behaves, but it's useful for modeling this wide class of problems. And then in the second part of the talk, I'm going to argue that we've identified a sufficiently simple enough model. It's broad in the sense that it can accommodate a lot of scenarios, but it's simple enough that we can actually identify mathematical structure in the problem. And I'm going to pull out a particular piece of structure that I'm going to call mixed monotonicity. And we'll see that it's an important dynamical property of models, of these models. And we can do some interesting kind of analysis with this property. And I'm going to conclude by changing gears a little bit and talking about partially autonomous traffic flow. So what happens when you introduce some autonomous vehicles into the network, and now you're studying traffic flow with these partially autonomous networks? OK, so a meta model of traffic flow. So let me start with a vignette. So suppose you're on a freeway. You're this blue car, and you're traveling along this freeway, and your goal is to head this way. You want to go on this spur of the traffic network. Right? And this spur is relatively uncongested. Right? So to make this concrete, here's the city of Atlanta. This is Georgia Tech. And if you're coming south, this is I-85. If you're coming south on I-85 towards Georgia Tech, but you actually want to head north on I-75, this is the situation you'll encounter in the evening rush hour. Right? North on I-75 is very uncongested. This is where you want to go. So you want to go on an uncongested route, but you're sitting here stuck in this traffic. This traffic, some of it wants to go straight. Some of it is going to take your route as well. But you're stuck dealing here with the congestion caused by this downstream congestion, right? So there's nothing you can do about it. So even though ultimately you're trying to get on this piece of the roadway that's not very crowded, you have to deal with the congestion along the way. And you have to sit through this congestion. And so what I would argue, and I think this is a pretty simple claim, is that any analysis and control method that you're trying to use to study this traffic behavior, this traffic flow network, it needs to account for this congestion you're experiencing. Right? It needs to account for the fact that congestion down here in Midtown Atlanta near Georgia Tech, this congestion down here, is back propagating and causing issues for you. Right? So this is an important, I would call this a phenomenon that you need to capture in your traffic flow model. But again, at the same time, you're hoping to find a model that's going to be simple enough so that you can say something concrete about how traffic flow is going to behave for you as a user of this road without necessarily having to run large-scale simulations or even small-scale simulations to get a sense of what's happening in the network. And so that's what we're going to be after today, is developing this model. OK, so with this kind of intuition in mind, let's make this problem a little bit more mathematically concrete. So this will be, these next few slides will be the most mathematically dense part of the talk, I would say. OK, so let's say we're after a meta model of traffic flow. We want to be able to model traffic, say, on a freeway network, but we want to be able to capture the types of phenomena I just described, these congestion effects in traffic flow. So I'm going to suggest, as many people have done in the traffic flow literature, that we track the evolution of traffic density over time. And we're going to spatially compartmentalize our traffic network so that we get some sort of network of links like this. And what we're going to do is we're going to track the density, or say the number of vehicles on every link in this network, right? And we want to be able to track them over time, right? We're thinking of tracking this on the scale of minutes or hours. Okay? So we want to see, for example, that if you get a congestion downstream, eventually you'll get congestion on this link, et cetera, right? And that will cause you to have this congestion issue that we just described on the previous slide. So we'll call this entire collection of links that you have script L, and we'll say that the vector x denotes your densities on your links over time. So let's take a look at an isolated link in this network. So let's say your link L, and we want to write down the dynamics for the density on link L. So this is x sub L dot, right? So this is the change in density for vehicles on this link. The equations come from, again, a physical property of traffic flow. They're going to come from conservation of mass equations. So for this particular example, we have traffic flow coming into link L from two upstream links, this link K, and then we'll call this an on-ramp, and we won't model it explicitly, but there's traffic coming from this green link as well. And then traffic is flowing downstream from link L to link J at some flow rate, right? And so we can give these names. We'll call F sub K to L, traffic flow from K to L, F sub L sub J, to J as traffic flow from L to J. And then we'll call F kind of arrow L just this exogenous flow coming from this on-ramp. And so if you wanted to write down this equation, you would have that the density change for link L is simply the incoming flow from link K minus the outgoing flow to link J, plus any flow that's coming into link L from outside the network, right? And in its most general form, this is why we're going to call this a meta model, these flow functions will be a function of the entire state of the system. For example, the flow from link L to link J, in most realistic scenarios, is going to depend on both the density on link L and the density on link J, right? Maybe not other links in the network, but we can write it in sort of this most general form, thinking that it's going to be a function of the whole state vector. OK, so this is the sort of dynamics you would expect to see in this simple model, or in this simple example where we have sort of 3 collinear links. These are the dynamics you would want to see. So how could we generalize this if we wanted to write and construct a meta model for an entire traffic flow system? So here's how we'll do it. There's some perhaps, so the notation gets a little hairier because we want to keep track of all of the links in the network. But really, the intuition is the same. The density change on any given link L is made up of several components. The first is the total incoming flow to this link, right? And so I just sum over all incoming flows K to L, right? This gives me all my incoming flow to link L, minus the total outgoing flow. So I just sum again over all L to J links, right? So this is the total outgoing flow from link L. And then I might have some exogenous exchange with the environment, right? So there might be links or driveways or on-ramps in my network I'm not modeling. And I can kind of move all that into an incoming exogenous flow and an outgoing exogenous flow, right? So I can write down this model for my traffic flow network. And now I have what I'm going to call a meta model for traffic flow. So I have how density changes on each link as a function of the flows on each link, right? OK, so far we've captured conservation of mass properties in our network. What we're going to do now is we're going to make some other explicit assumptions on how these flows behave that we're going to consider to capture the phenomena we're after in traffic flow networks. And I'm going to argue that it's a natural model, and then I'll show that a specific case of this model as we go along. Occasionally, I'm going to want to collapse this entire expression into one function. So when I write capital F, this is going to be the collection of total flows, the net flow for link L. OK? All right, so let me tell you some assumptions we would need on our meta model in order for it to be a reasonable model of traffic flow. I'm going to have 2 slides on this. The first assumption is going to be assumptions on net flow. So let's just and I've written them down. So here at the top, this is the same equation from the previous slide, copy and paste it to this slide. So this is our meta model. And here I'm listing 2 assumptions that I would argue are natural and are needed to capture the phenomenon you would want to see in a traffic flow network. These are assumptions on net flow. So let me unpack these expressions a little bit. So the first is a statement about the derivative with respect to state on link M of some quantity. What is this quantity? This is the total incoming flow to link L. Right? So think of, again, link L as sort of our main link that we're reasoning about. We want to say that the total incoming flow to link L, if you perturb the density on some upstream link of L, this total incoming flow is non-decreasing. Okay? So here's the picture. Here's link L. It has some total incoming flow caused by these upstream links, possibly some exogenous flow as well. If you were to increase the density on any one upstream link, you want this net flow to increase. That's a pretty reasonable assumption on the phenomenon you would want to consider reasonable for modeling traffic flow. Okay? So that's an assumption on the net upstream flow of a system. Now let's take a look at downstream flow. So if you, again, take a look at this total outgoing flow for any given link L. So now link L is on this side of the junction. And you want to look at the total outgoing flow of link L. You want this to be you want this derivative to be non-increasing with respect to the derivative of any other link at the junction, right? So this also makes sense, okay? So you have outgoing flow from link L. Now imagine you have outgoing links here. And imagine you increase the density on these links. They should cause congestion at your junction, and they should decrease the flow. Likewise, if you have sort of a competing link M, and you increase the density on link M, it should compete with the outgoing flow from link L, and you should have decreasing flow. So no matter what you choose for these flow functions F, I'm arguing you want them to satisfy these 2 properties to be reasonable for traffic flow. Okay, so this is the first properties we need for a meta model of traffic flow. Now let's reason a little bit about what this vignette we had, right? We had vehicles that were, in our vignette, we had this congestion effect that we're trying to capture in a traffic flow model. So let's see how we would capture that concretely with a mathematical equation. So this is what's called in traffic flow theory the first in, first out principle, right? Which, of course, is a term you've seen in computer science to understand queuing behavior, and that's where it comes from, is because in traffic flow you have a queuing type property where vehicles in general can't speed past other vehicles to get to these destinations, right? So here's the principle kind of written out. First in, first out node model has the following properties. First, congestion blocks upstream traffic regardless of destination, right? This is what we're trying to capture. We're trying to capture the fact that these vehicles, even though they're headed a different direction than you, they're going to cause congestion for you, right? The second comment is that empirically, you can find in the literature evidence of this FIFO model, this first in, first out model, even on multi-lane interstates, where you might say, well, there's so many lanes that the traffic's going to naturally split up, and you're not going to have this property. Turns out that's usually not the case. You at least get some version of this FIFO property, this first in, first out property, even on these multi-lane freeways, right? So mathematically, how do we want to capture this first in, first out property? Well, it's going to look like the following. If you take a look at the flow from link K to some outgoing link L, right? So think of this as you. You're trying to go from link K to link L, right? And then you have some other link M, which is an alternative destination, maybe for some other vehicles that are on link K. Now, so we'll call L and M adjacent. And suppose you now take a look at the derivative of this flow from K to L with respect to the density on link M. You want this to be a non-increasing function for all triplets of links K, L, and M satisfying these properties. Again, this is the intuitive phenomenon we're trying to capture. We're trying to say if you increase density on link M, so you make M even more congested, it should decrease the flow from link K to link L, because it's going to cause more blockage upstream, right? So these are the assumptions that if you give me a traffic flow model and you populate these flow functions with whatever you want to choose, so long as they satisfy these general flow properties, I would argue this is a reasonable meta model of traffic flow. OK, so let's spend at least one slide making this a bit more concrete. So let's take a look at this particular situation I've been alluding to. So you have one road that splits into two roads, right? This is our vignette. You have an upstream link 1 that splits to two downstream links 2 and 3. Okay? So this is, again, something we're adopting from sort of the standard literature on traffic flow modeling. It's this idea that traffic links can be modeled as having demands and supply functions. And the flow at the interface between two links is a function of these demand and these supply functions. So let me explain what I mean by that. Every link has a demand function d sub I that's an increasing function in the state of your state of that link, so increasing in the density of that link. And this function represents the volume of vehicles that are wanting to flow downstream, right? So you have more cars on a link. There are more cars trying to get downstream on that link, right? This is the demand function of that link. It's an increasing function. Symmetrically, every link has a supply function. This is the supply of available space on that link, and it's decreasing in density, right? So when there are no cars present and x sub I is 0, the supply function is as large as it can be. And then as this density increases and approaches some jam density, this is the maximum capacity of a link, this supply function decreases, right? So as you have more cars, you have less space, right, for vehicles on that link. And the fundamental principle of most of these cell transmission model-based models of traffic flow is that the flow at the interface of two links can't exceed the demand of the upstream link or the supply of the downstream link. So again, how would we write that mathematically? Well, first, we need to understand how traffic splits at this junction. And we're going to do that in the following way. We'll assume that there are fixed turn ratios that divide traffic between links 2 and links 3. Right? And that you could get from, for example, some sort of mapping app where you just take a look at where traffic goes when it gets to this junction. So maybe 80% of the traffic goes from link 1 to link 2, 20% of the traffic goes from link 1 to link 3. Right? These turning ratios are actually pretty stable and they're pretty static for most traffic networks over time. Right? Most people's evening commutes are fairly fixed, and for example, or morning commutes are fairly fixed. And so you get pretty fixed turning ratios at these junctions. OK, so how could we instantiate a particular version of our meta model using this idea of demand and supply functions and turning ratios? So here's one way to do it. This is, I would argue, a pretty natural way of doing it. You take a look and you define your outgoing flow from link 1 to be the total flow that's exiting link 1. Concretely, that's the flow from link 1 to link 2, the flow from link 1 to link 3, and possibly if any vehicles exit the network, maybe an off-ramp, you could add that there. And we can define this outgoing flow as the minimum of 3 quantities. It'll be the minimum of the demand on link 1. Okay? So this is the number of vehicles on link 1 that want to flow downstream. Minimized with the downstream supply of the 2 links, link 2 and link 3. Right? So if there's a lot of congestion on link 2, this supply constraint will shrink, and it'll become the minimizer in this expression. Okay? But we have to modulate these supply functions with the turning ratios, because only a fraction of vehicles will be headed to link 2. And so if you think of moving this beta to the left, we want to make sure that beta times the outgoing flow of link 1, beta sub 1, 2 times the outgoing flow of link 1 doesn't exceed the supply of link 2. Okay? And as I just argued, once you have the outgoing flow of link 1, here's the model you would want to implement for the flow from link 1 to link 2. It should be beta 1, 2 times the outgoing flow of link 1. And the flow from 1 to 3 should be beta 1, 3 times the outgoing flow of link 1. Okay? So what does this model look like? If you take a look at, for example, in a situation where you have light traffic downstream, there aren't many vehicles on link 2 or link 3. The demand of link 1 will be the minimizer in this expression, and the total traffic on link 1 will dictate the flow downstream of link 1. On the other hand, and this is probably the condition that we're more interested in capturing, what happens when the supply becomes constrained downstream? What happens when you have congestion on a link downstream? So for example, in particular on link 2, then this becomes the minimizer in this expression, and link 2 becomes the driving force behind this outgoing flow of link 1. Okay, so here's an example. Again, this is a specific example of an instantiation of our meta model for traffic flow. Okay. Okay, great. So that concludes the first part of the talk. We now have a mathematical meta model in our pockets for traffic flow. What can we do with that? So in the next part of this talk, I'm going to argue that this meta model we've constructed with these assumptions on flow that we've pointed out, it actually satisfies, it has a lot of structure in it. It has an interesting structural property called mixed monotonicity. And this property, mixed monotonicity, we can actually use to say general statements about traffic flow networks that satisfy these meta model properties. And as I've argued, I think these are the types of models you would want for traffic flow networks. OK, so I need to do a little bit of dynamical systems background here. So suppose you have a system that looks like this. X dot equals f of x. So this is an ordinary differential equation. It defines a dynamical system, a continuous time dynamical system, right? This is a definition up here. This system is said to be monotone if the following property holds. If you take 2 initial conditions, x at time 0 and y at time 0, and again, x and y are vectors. And so when I say x at time 0 is less than y at time 0, I mean that each element is less than or equal to the element on the other side, right? So if x is a vector of densities and y is a vector of densities, x and y are ordered if each of these densities satisfies this inequality. OK, so back to our definition. The system is said to be monotone of this ordering property. If you're ordered in initial conditions, you maintain this ordering property over time, right? So if you start with, say, larger densities in every link, then you maintain larger densities on link. If your system satisfies that property, it would be said to be monotone. A necessary and sufficient condition for monotonicity you can write in terms of these partial derivatives. You want the partial derivative of f of I with respect to x of j to be nowhere negative for any pair I and j not equal, right? So again, if you think of this as your state space for your system, and you take an initial condition x naught, this is a 2-dimensional system. Y naught satisfies this ordering property so long as it lies in this kind of rectangle here, this quadrant above x naught. And if your system's monotone, you maintain this partial ordering over time. And as the system evolves over time, y of t will always be above x of t as it flows along the system. OK? So that's monotonicity. This is a well-known property in dynamical systems theory. It implies strong properties for equilibria and convergence, and it's been known for about a decade now that traffic flow networks without diverging junctions are monotone. Okay? So again, remember, our vignette is a diverging junction. We're talking about traffic that needs to go in 2 different directions. So this does not cover our particular congestion propagation example, but it does cover a lot of examples, right? So maybe just a linear segment, a freeway with some on-ramps. This would satisfy this property that doesn't have diverging junctions, and the dynamics on this system are monotone. Okay, so that's an interesting observation. It's been known now for about a decade, as I said. So the question is, what can you do when you don't satisfy this property, when you have diverging junctions? And again, this is what we're kind of interested in studying. We want to be able to say something about this vignette we opened with. We want to say something about how traffic behaves in that scenario. So let me move to this slide. So what we've done in our work is we've introduced a new concept of mixed monotone systems. So we didn't introduce the idea of mixed monotonicity, but it hadn't really been applied to too many interesting systems before. So what we did is we took this property, we've written it in this form for continuous time systems, and we've shown that we can use it to study traffic flow networks. So let me work through this definition a little bit. It's a little bit more complicated than our definition for monotone systems theory. But again, it's designed to capture a lot of the same features as monotone systems theory. OK, so a system x dot equals f of x, again, this is a dynamical system, is mixed monotone if you can find what's known as a decomposition function g, which takes 2 arguments, a vector x and another vector y, and this function g satisfies the following 3 properties. The first is that if I actually substitute in the same vector x for both of these arguments, I should get back out my original dynamical system f of x, my vector field f of x. And this should hold for all of x. So this property tells us that this decomposition function somehow captures all of the information of our original system. So we don't lose anything. There's no information loss by taking a look at this decomposition function. Then the next 2 properties, let me explain what they are. The first is that if you take a look at the partial derivative of g of I with respect to any vector with any element x of j, this should be non-negative for any x and y, and I not equal to j. And the second property is that if I take the derivative of g of I with respect to y of j, this should be non-positive for any pair of vectors x and y, and now for all I of j. Okay? And let me just drive home the point that this is an extension of our definition for monotone systems, because in the special case when our system is monotone, we can take our decomposition function to simply be equal to our vector field f of x. And you can see that then this condition doesn't apply. We don't need to worry about this condition, and we recover condition 2, which was exactly this derivative condition I had on the previous slide. Okay? So mixed monotonicity, now a generalization of monotone systems theory. OK, so let me tell you a sufficient condition for mixed monotonicity. This is actually not a necessary and sufficient condition. So in the monotone systems case, we had a necessary and sufficient condition. Let me now just tell you a sufficient condition for mixed monotonicity. And it's as follows. If you take a look at these partial derivatives, fi with respect to xj, you want to be able to find a delta ij, which is either 1 or -1, so that this product is always non-negative for all x, right? OK, so this is actually a pretty easy condition to reword. It just means that if you take a look at this partial derivative for any I not equal to j, its sign, sign, should not change over your state space, right? It should always either be positive or it should be negative, OK? So again, in the monotone case, we needed this sign to always be positive. But in the mixed monotone case, we can take either positive or negative, all right? So I'm telling you this is a sufficient condition for mixed monotonicity. So somehow I should be able to connect it to this definition I showed you on the previous slide. And I can do that. And I can do that by constructing explicitly this decomposition function. It's actually pretty straightforward. You just take your vector field f of I, which is, of course, takes as arguments x sub 1, x sub 2, up to x sub n, say, if your system has n dimensions. Anywhere where I saw x sub j, I take it out, I put y of j, right? I do this for every f of I, then I stack them up. I call this my decomposition function. And you'll see that if f of I satisfied this property up here, and I do this construction for any delta ij equal to -1, then this function g will satisfy the properties of a decomposition function that I showed you on the previous slide. Okay? So that's how I would show that this is indeed a sufficient condition for mixed monotonicity. All right, so let's connect this back to traffic flow. So what does this do for us? So if I return to our diverging junction model, so again, same picture. We're studying in particular the scenario where we have this congestion regime downstream. What happens in this particular case? We have that the outgoing flow from link 1, which recall was a minimization of 3 quantities, it now is actually equal to this particular quantity, 1 over beta 1 to S2 exa 2. This is because link 2 is congested. It's the driving force behind the flow that's allowed from link 1 downstream. Okay? So what happens in this particular case? Well, if we substitute now this expression in for f of 1 outgoing flow, we see that the flow from link 1 to link 2 is equal to the supply of link 2. That makes sense. Link 2 is congested. It's the driving force behind this flow. The flow coming into link 2 is equal to its supply. But what's interesting is what happens to the flow from link 1 to link 3. This is you. You're trying to go from link 1 to link 3. Is it depends on the supply of link 2, which is kind of interesting because we're talking about the flow from link 1 to link 3 has nothing to do with link 2, maybe on its face, but of course in reality it does because you're concerned about the congestion on link 2. This is exactly the phenomenon we've been explaining. You're waiting in traffic. You're trying to go somewhere very different than everybody else is trying to go, but your fate is intertwined because you both are waiting for this downstream congestion to clear. OK, so as a first cut, let's just confirm that our system is not monotone. It doesn't satisfy the property of monotonicity that we described several slides ago. We can take a look in particular. For this particular case, we'll look at the flow f of 3. And we'll see, again, it's equal to this function here, the ratio of betas times the supply, minus some outgoing flow from link 3. But that's not what's important here. So there's some flow exiting, but that's not what's important to us. If we take the partial derivative of this flow with respect to x2, we'll get a negative quantity. This would immediately breaks monotonicity. We can't have this monotone property anymore. So here's the question, is this system mixed monotone? Well, you can probably guess that the answer is going to be yes. Otherwise, I wouldn't have gone through this effort to define mixed monotonicity for you. So let me just write that down as a theorem. So this is a theorem we've proved a couple years ago now, is that traffic flow networks have mixed monotone dynamics. So if you don't have any diverging junctions, it's monotone. But even if you have diverging junctions, you at least have this mixed monotonicity property, which generalizes very nicely monotone systems theory and gives you this kind of new tool set at your disposal. I'll skip the proof. The proof is basically using the intuition I described about the sufficient condition for mixed monotonicity. OK, that's great. Let me just quickly explain how we can use this property, mixed monotonicity. OK, so great. Now you know that traffic flow is mixed monotone. What can you do with it? Well, here's one thing we've done with it. We've used mixed monotonicity to construct what we call an embedding system. So you just take your decomposition function, you take 2 copies of it, you swap the arguments, and you call this entire system the embedding system. It has twice as many states as your original system, x dot equals f of x. But it has these interesting properties. The first property is that it's actually now this embedding system is a monotone system. OK, I had to play a couple of tricks. I have to redefine what I mean by a partial order on states, but that's easy. And here's the mathematical expression for that. I just, instead of saying I'm partially ordered with respect to the northeast quadrant, if you think of kind of regular monotonicity as being with respect to the northeast quadrant, this embedding system is with respect to the southeast quadrant. So I just reorder my y variables. That's straightforward. So that's important. I now get the power of monotone systems theory I can apply to this embedding system, which I can construct for any mixed monotone system. The other important feature is that on a particular subspace, submanifold of this higher dimensional embedding system, actually recover my original dynamical system. So if I can say something about this entire embedding system, I can then also apply that to what's happening on this subspace. Now, of course, it doesn't go the other direction. If I'm unable to say something about, for example, stability properties of this embedding system, I can't say for sure what's happening on this lower dimensional submanifold. But I do get this nice one-directional ability to say something interesting about the system. So here's the theorem. For traffic flow networks that don't have cycles, and with what's known as feasible input flows, so the total incoming flow isn't too extreme into your network, then the equilibrium is unique for the system, and it is globally asymptotically stable. So for this entire meta model of traffic flow models, for any instantiation of this meta model, so long as your network doesn't have cycles and your feasible input flow is low enough, we can use the mixed monotonicity property to establish global asymptotic stability of a particular equilibrium. And here's just that picture of that happening for, again, our kind of motif example of this diverging junction with some particular numerical results. We see convergence to a unique equilibrium. So that's just sort of a hint at what we can use this mixed monotone property for. OK, so I want to switch gears now a little bit in the time I have remaining and talk about a slightly different problem. What happens in traffic flow systems when we introduce autonomous vehicles? What should we expect to change about our system dynamics? OK, so we want to introduce autonomy. So I want to make a couple points. The first is that this is not a futuristic assumption, right? Autonomy is already here, right? Of course, I'm not talking about fully autonomous cars that can drive you without steering wheels. Those are on their way, and they'll get here someday, maybe. But autonomy in the sense that we already have advanced technology to do lane keeping. We have adaptive cruise control technology, which I'll talk quite a bit more about in the next few slides. Automatic parking, right? So we have these technologies. You might call them semi-autonomous technologies. These exist. You can buy these tomorrow in many different versions of a car. The point I want to make first is that people kind of, when they say, oh, autonomous cars are here, a lot of times the subtext is that imagine how much better our lives are going to be. The first comment I want to make is that improvement is definitely not guaranteed. So here's 3 recent news clippings where kind of semi-autonomous technologies and sort of their closely related kin are not improving the situation. So here's an example of a Google car that was pulled over for going too slow, right? OK, so that's not going to help if your self-driving car drives at 10 miles an hour. OK, that's not a super impressive feat, right? Here are 2 examples. These don't have self-driving cars in them, but people often talk about using self-driving cars to, for example, navigate themselves through cities, or possibly to do automatic taxi pickups and drop-offs. Here's 2 examples where this can quickly become bad, right? It can really make the situation worse. So there's no guarantee that autonomous cars are going to make our lives better. And so here's really the research question here, I think, for researchers in this field. How do you realize the promise of increased safety? So everybody talks about how much safer the Tesla is than, say, other cars. How do you realize this increased safety without compromising mobility? Okay? I can make the transportation system quite safe if I make everybody drive under 2 miles an hour, right? But that doesn't help anybody. So the question is, how do I balance this trade-off between safety and mobility? And in fact, I want to argue it's not a trade-off. I think you can increase both, but you have to be smart about how you do it. All right, so I want to talk about a problem we've been studying in adaptive cruise control technology. So here's the mathematical model we're going to take a look at. So suppose you have a single street, and you have what I'm going to call regular vehicles on them. So these are your regular cars, no technologies in them. You might expect to see something like 2,000 vehicles per hour throughput on this road. Okay, if you open up the highway capacity manual, it'll tell you roughly 2,000 vehicles per hour on this road. If you then assume that these technologies are equipped with adaptive cruise control technologies, and here's a video of a particular adaptive cruise control technology from Subaru, a particular manufacturer, if you assume that they have this ability to maintain these headways adaptively, and you also assume that they do it aggressively, which is a bit of a leap, but kind of a back-of-the-envelope calculation, and you can find this in multiple papers, you should expect to see roughly a 3-fold increase in the capacity of that link. Okay? Now you can get 3 times as many cars going on this link if they all have this technology. Okay? But here's the question. What happens when you have mixed autonomy? You have some autonomous cars and some regular cars on the network. What's the answer to this? And again, I just want to highlight, there are 25 plus car manufacturers that produce ACC-capable cars today. So this is a relevant and important question. So we have some preliminary work that shows that, perhaps unsurprisingly, you'll see a nonlinear relationship between the fraction of autonomous cars you have in the network and the increased throughput. Okay? So here's, for example, a reasonable plot of what you would expect to see under some particular assumptions on headways and the stochastic processes of the cars. That's not too important. What's important is you see this nonlinear relationship. As the fraction of vehicles with autonomy moves from 0 to 100%, you see the throughput increase from 2,000 vehicles to 6,000 vehicles. That makes sense with our first 2 pictures. And then you see this nonlinear curve here, right? And what I want to point out is that the benefits they're not, because it's nonlinear, you have this interesting property where the benefits actually increase as the fraction of autonomous vehicles increase, right? Going from 0 to 20%, sure, you'll see some improvements. But going from 60 to 80%, you'll see a lot of improvement, right? So the benefits will be increasing over time. The other important observation is that if you could somehow control the number of autonomous vehicles on a road versus the number of regular vehicles on a road, you have these new opportunities to kind of tweak the throughput possible on that link. And that's what we've been studying in these last few slides that I want to cover before wrapping up. So, so just a few slides on this. So I want to exploit this partial autonomy for optimal routing. So here's the question. Can we realize traffic improvement by actively routing smart versus regular vehicles? Okay. Here's the fundamental property we're trying to trade off. If I can increase the throughput on a link, I can reduce the delay on that link. Okay. This is what we're trying to take advantage of. And the metric we're going to use to describe how good we're doing is this well-known idea of price of anarchy, which you probably are familiar with in at least some sort of colloquial context, is that the price of anarchy is the ratio of the worst case delay you could see in a network, say, an entire network of Atlanta, with selfish routing, divided by the best case delay you would see with optimal routing. Okay? This is called the price of anarchy. Some known facts. The price of anarchy is known to be bounded for traffic flow networks when you only have one type of car, so say regular cars. It's known to be bounded by 4/3. This also sort of explains why there's only so much benefit you can expect to see by really doing a smart job routing cars through a network, is that if you just let them do their own thing, and they do it, and so every car kind of locally optimizes its route, in the worst case, you're only going to make things worse by a factor of 4/3. Okay, so our question, and this is joint work with some of my collaborators at UC Santa Barbara, is what happens in this partially autonomous case? And it's actually a very interesting story. So let me spend 2 slides talking about this prototypical example. Say you have a source node and a destination node, and you have 2 roads on between these 2 nodes. And this is kind of standard for these optimal routing problems. You can actually get a lot for the general case by studying this simplified case. And here's what's happening. We have some total amount of regular cars, and we want to split them on these 2 roads. And we'll say xi is the regular cars going on the top road, x1, and then x2 is the regular cars going on the bottom road. And we also have smart cars that we want to split between the 2 roads. And we're going to assume that the delay on the road is somehow a fraction of both the regular cars and the smart cars. Okay? So that makes sense. Here's our particular delay model we're going to assume. And you can actually derive this delay model from that graph I showed you, that nonlinear relationship. You actually get under some reasonable assumptions, you get some nice affine delay model. And here's what the delay on a link looks like. You have some free flow delay, which we'll call B. And that delay increases with respect to the total cars on the network. So that's the regular cars plus the smart cars. But the regular cars, you incur a penalty because they're worse. They can't maintain these close headways. And so this is the kind of affine delay model you get. Okay? So this is delay per vehicle, but you have to kind of weight the regular cars because they're worse than the smart cars. Okay? And again, if we're talking about the price of anarchy, the optimal router is interested in this quantity here. You want to take the cost on link 1 times the total cars that are on link 1 plus the cost of link 2 times the total cars on link 2. The selfish routing situation, Wardrop, Nash equilibrium, sort of the same ideas. The cars are just interested in making sure that their costs are the same. I can't do better if I switch to a different road, right? So these are sort of the 2 things we're looking at. So let me tell you what happens for the case for this simple network with some particular cost function. So let's make, admittedly, particularly simple cost functions, but they're within our class of affine delay functions. So the cost of this top road is free. Well, no, sorry, it has a cost of link 1. That's the free flow cost, but it's free for additional vehicles. I mean, the more cars you put on it, doesn't cost you extra. On this lower link, we'll assume that the cost is just a function of the regular cars, and that somehow smart cars, the cost is free, right? Okay, so again, it's kind of simplified, but it's definitely within our class of systems. Now suppose you have 1/2 units of smart vehicles, okay? And maybe a unit's 1,000 cars or something like that. You have 1/2 unit of smart cars that you're trying to route between these 2 roads, and you have 1/2 gamma regular cars you're trying to route. And say gamma is some number greater than 2. Okay? What's going to happen in the selfish case? If these cars are selfish, you can reason about this, and you'll see that in this case, all the cars are going to take this lower road. Okay? So what's the total cost going to be? It's going to be gamma times the number of regular cars, so that's 1 over 2 gamma, times the total cars on that link, and this is the quantity you get. Okay? Now, what if you were smart? What if you're the social optimizer and you're trying to optimize this cost? What would you do? You would actually split the traffic. You would put all the regular cars on the top, all the smart cars on the bottom. And what delay would you see? You would see something like this. The smart cars don't have to pay anything, and the regular cars pay cost of 1, and you get a cost of 1 over 2 over gamma. Okay? And if you compute the price of anarchy in this case, you get this quantity, gamma plus 1 over 2. And what's interesting here is as I increase gamma, I can make this price of anarchy as bad as I want it to be. Right? So of course, for fixed gamma, this price of anarchy is fixed, but I can make it arbitrarily bad. Right? So the price of anarchy can be arbitrarily large with autonomous vehicles. Okay? And of course, this contrasts with the known bound of 4/3 when there are no smart vehicles. So this tells us, theoretically, the situation is going to be very different when I have autonomous vehicles in our system. So the good news is that we can provide some bounds on the price of anarchy. So this is recent work. This is a theorem that's going to appear in ACC this summer. So again, the price of anarchy is going to depend on the sort of the extra penalty you have associated with regular cars. So let's take a look again at our affine delay model. This was the affine delay model we had. K sub I was that extra penalty for being a regular car instead of a smart car. If you take a look at an arbitrary network, so the entire city of Atlanta, say, or the entire city of Seattle, and you take a look at this asymmetry, and you can imagine this asymmetry might be a function of the road geometry or how many sensors are on the road, that sort of thing. And if you let capital K just be kind of this maximum asymmetry in your network, and I want to emphasize that for adaptive cruise control, most people think that this penalty is going to be in the order of 2 or 3, say. If you have an arbitrary network and this penalty, this maximum penalty is less than 4, then we have shown that the price of anarchy is less than or equal to 4 over 4 minus K. Okay? This is the theorem we have. So let me highlight a few features of this. First is it recovers this really well-known 4/3 result for the particular case when K equals 1. When K equals 1, there is no penalty for being a regular car. It's just like having one type of car in the network, so we get our classic result. We also know that it's tight for K equals 2, but we don't know if it's tight in general, and in fact, we don't think it is. We actually think that there probably exists a bound for K larger than 4, but we haven't been able to prove it yet. But we can prove it in this case. The last comment I want to make is that we actually have similar bounds for a quantity known as the bi-criteria, which is a measure of how much extra traffic you can put on the network with this optimal routing. And so I won't go into that, but I just want to emphasize that we do have bounds on that as well for the case when K equals less than 4. So I think this is an interesting result, and we're trying to understand what to do in the case when K is greater than 4. OK. So that ends my talk. That's all the parts I had in my talk. So let me just highlight kind of the 3 takeaway messages here. The first is I think there's a need for mathematical models in traffic flow and in other domains that are amenable to formal analysis. It's great that we have so much data at our disposal. But the question is, for many physical systems, we want to figure out how to marry that data with models. And I think deriving meta models or concrete models that one can actually get their hands on and do some math with, I think is very important. Why is that important? Because I think you'll find there are a lot of structural properties, such as mixed monotonicity, that show up and these systems, and they're going to be key if you want to say anything formal about how your system is going to behave. The last comment is sort of specific to traffic flow networks, but also for other physical networks, I suppose. As we see more and more autonomy entering these systems, they're going to change the system-level ability to control the network and system-level analysis techniques quite substantially. And I think we're going to need a whole new suite of tools to understand these problems. I want to highlight something that's not in this talk that's a big part of my research, but I didn't have time to talk about it, is that I use these formal models and these formal structural properties for formal methods of traffic systems. So to apply these formal techniques from computer science, if you're familiar with things like temporal logic to these systems. And again, these structural properties are key for doing these types of formal techniques on these systems. And so if you're interested in that, I can talk to you more about that offline, but I just didn't have a chance to talk about it in this talk. And with that, I'll thank you. And there's a few sponsors that are sort of involved with some of the work that I showed on this slide. And thanks a lot for your attention. Appreciate it.
So thanks, Sam. Are there any questions? If not, I have a few. So you have the slide or the part of your talk where you say that you get some guarantees for cases where you don't have cycles in the network. So that basically will just apply on like freeways and things like that?
So it sort of depends. Even if your network has cycles in it, if you sort of assume that, like, say in the morning rush hour, people tend to go one direction sort of things, the topology that exists for that morning rush hour, you might be able to model as an acyclic graph, perhaps.
And is there any hope to extending it to the?
Yeah, there is definitely hope. I mean, I think there are answers there. Things get much more complicated when there are cycles for many reasons. But yeah, there is some hope there. I think we're going to need more tools in monotonicity, but I think things can be done there.
The other question I have, if no one else has a question, okay. So the last part that you talked about, have you made the connections between some of the recent work in routing games on things like altruism and tolling? Well, tolling's been around for a while, but and we even have some recent work interpreting that kind of congestion that you have as like a multiplicative uncertainty.
Okay.
And actually, we have an ACC paper with exactly the same price of anarchy bound.
Oh, really?
Yeah, we're probably in the same session.
Okay.
But I'm just curious, so some of the stuff that we were finding is some interesting parallels between just different interpretations of the same kind of result.
Okay, we should talk about this more offline.
Okay.
No, I mean, so this is still, kind of early work. I showed the picture of the grad student who's been spending a lot of time thinking about this. I think there's a lot of interesting problems when you kind of look at it this way. But no, we really haven't looked at it much further than that.
Okay.
Yeah.
All right, well, if there's no more questions, we'll just thank the speaker again.